Good morning or afternoon, depending on what part of the world you all are in. This is Jeff Eaton, and on behalf of Dr. Julie Seaton of the Military Operations Research Society and Commander Walter Grange and myself from the Military Application Society of Informs, we want to welcome you to the latest in our series of bi-monthly student webinars. Today we're honored to have Dr. Alexander Newman, who is going to talk to us about operations research at the Colorado School of Mines. A few ground rules before we kick this thing off. Just want to remind everyone to mute their phones, and there will be time for questions at the end. And what we'd like you to do is, for questions, just go ahead and type those into the chat feature of the WebEx, and Commander Walter Grange will read those off at the end to Dr. Newman. Dr. Newman is currently the Associate Professor at the Colorado School of Mines, and prior to that has taught at the Naval Postgraduate School. She specializes in mixed integer programming, combinatorial optimization, and linear programming, and has applied this wealth of knowledge to various transportation and logistics, military operations, and mining problems. So without further ado, I'd like to turn it over to Dr. Newman.
Okay, thank you. Can you hear me?
Loud and clear.
All right, very good. So I'll talk today about some military work that I've done, some of which I actually started at the Naval Postgraduate School and finished once I got here. Other problems are new. So this is why I have that some of the military problems I'll present solutions for, and others are still works in progress. And if anyone is interested, I can also point them to papers on the subject later. So, all right, let's see. All right, so first of all, I'll just give a little bit of an outline of the types of problems I'll be discussing. I'm trying to cover, I guess, 4 services. I will talk first about some kind of older work on capital budgeting for the U.S. Air Force Space Command. This is work that's been published in interfaces with some of my colleagues at NPS and a former Air Force officer. I'll then talk about a personnel planning model that was used for a long time. I think they're just transitioning to a new one, but this is work that I did with an Army student of mine here at the School of Mines. I'll then discuss a scheduling model for helicopter deployment and maintenance for the Coast Guard, and the Coast Guard officer and I worked on this model specifically for the aircraft at Clearwater Air Station in Florida. And then I'll discuss something done with a host of colleagues of mine at Naval Postgraduate School. This was some work that I did the bulk of while I was a research assistant professor in the OR department at NPS, and this would be assigning Tomahawk cruise missiles to surface ships and submarines. And then I'll discuss a little bit of more current work. I have an Air Force officer who is currently in Korea, but finished his PhD here, and we're working on implementing his model for course scheduling at the Air Force Academy. And then the other 2 topics I'll discuss are some work, first of all, with Marvin King, who's a major in the Army, and Professor Amanda Herring, who's a statistician here at Mines, dealing with optimizing counterinsurgency requirements. And finally, some work with another Army officer of mine here at Mines, and my first PhD student ever, who's now on the faculty at NPS in the OR department, Lee Ewing. And we're dealing with kind of a, I'd say, a successor to the BRAC type models, the base realignment and closure. And so Michael Peter is working on that. So kind of 4 older topics that have been published, and then 3 more recent topics we're currently working on. So this is a bit to get done in the allotted time, so clearly I can't do justice to every topic, but I'll try to cover them in some detail to give you an idea. All right, so the first topic would be how the Air Force Space Command optimizes long-term investment in space systems. The idea being that the Space Command spends a lot of money every year acquiring and developing mainly launch vehicles and space systems, since they're at the Space Command. And the idea is that the systems that are in orbit have to meet defensive and offensive requirements they have to remain not just operational, but there needs to be some sort of interoperability or some notion of, you know, the mix of systems acting synergistically with each other. So this model spans several decades, and then the notion is that we want to kind of project the needs of the Air Force over this time frame within the capital budgeting constraints. The other thing is that we're interested in a certain goal, and this goal here is to minimize the shortfall between what we'd like to capture in terms of these measures of national security and what we're actually able to cover based on the systems that we acquire and set forth. So. All right, so just a little bit of background on the systems themselves. Some of these systems are clearly what you'd think of in terms of launchers and things that get launched, such as the satellites and space-based lasers and space-based radars and so forth. There are also vehicles, terrestrial vehicles and so forth that they would use. There's also just things to keep up the morale of the staff. And so these are also included in the model. There are not only systems, but also research and development initiatives, and so those might be funded in terms of trying to provide some future capabilities to the Air Force. So the systems themselves don't just operate in isolation, and so one can think of the systems really as relating to other systems in one of the three following ways. Either a system A is operating and B must be operational the entire time that A is operational. So B1 is not allowed to operate without A's operation. The second is that B has to start operating at some point. It's got to be operational during some point at which A is operational. That would be B2. But it doesn't have to overlap entirely with A's operation. So A can stop operating and B2 can continue operating. The other types of systems we have is as soon as A stops operating, we have to acquire a certain system, B3. So B3 has to follow on from the operation of A. And so these, you know, different characteristics depend on, you know, the systems being incorporated. But we have to incorporate these interoperability characteristics into the model. So here's a sample space system here, and this is launching a satellite from Cape Canaveral. All right, so I have in some of these some math. I won't spend too long on this, but the notion is that we have, you know, a variety of constraints expressing kind of in a mixed integer or linear programming format what we need to do. So, you know, we have these rather descriptive variables in this particular formulation. We're trying to figure out various systems S to select that would start in year Y under bar and stop in year Y over bar. And of course, for every system, we can have at most one time window, Y under bar, Y over bar, during which the system's operating. And then we have constraints that deal, you know, with measuring the extent to which various task coverage is actually acquired based on the selection of various systems. And you notice a little small dot over the relational operator. This means the constraint is elasticized. So if we don't cover all that, then we get a penalty. We incur a penalty for not providing coverage. And then we have things like interdependency between systems. So we have to select systems with launch requirements such that we have the requisite launchers. And if we don't have the requisite launchers, we can't select the systems. And so we have these types of constraints, the third and fourth on slide 7. You see two different types of budget constraints here. You also see dots over the relational operators. And so the idea there is that in every year, we need to ensure that we select some reasonable number of systems to stay within our budget. But some types of systems, namely the launchers, are extremely lumpy in their costs. And so because of that, we put these launchers in an epoch budget constraint instead. This spans 5 years instead of a single year, so that we're not worried about putting them in a single year's budget and then not being able to buy anything else for that year because, you know, we used up our whole budget buying a single launcher. And then you see that we have various constraints dealing with the characteristics I showed a few slides ago on the systems. So the systems that need to operate concurrently with each other, or one system needs to be a prerequisite to another system, or the systems have to operate contiguously. So as soon as one stops, the next one has to start. Of course, these are all identified a priori based on what the systems are, but we need to incorporate this into the model. So what we do with that one is we go ahead and we minimize the penalties associated with the deviations from the constraints that we've marked with a dot over the relational operator. And later on, I'll show you some results, well, some solution techniques and some results. So we'll hold that thought for a minute and go on to the Army model, the personnel planning model that Dan Shrimpton and I put together to designate career fields for officers. And so I hear that this is, has been used, but I hear that it's now being replaced with another system, so it's a slightly dated work. But the idea behind this is that in 1999, the Army instituted a new career progression pattern for its officers to designate them into specialized roles. Either they'd remain in their basic branch or they would elect to go into a functional area such as a foreign area officer, of course an operations research analyst. There are also psychologists and people who are experts in language and so on and so forth. And so upon their promotion to major, they were either going to elect to stay in their basic branch or assume one of these functional areas. And so this model that we have assigns the officers to career fields subject to the staffing requirements of the Army and the availability of officers based on their preferences and also their kind of capabilities. And we wanted to go ahead and maximize the sum of order of merit list scores that were based on the officers' kind of qualifications and rankings given by senior personnel. The scores were slightly difficult to incorporate in the model because we needed to be a little bit subjective about what we were doing. So the idea was that the board, consisting of colonels and generals and so forth, would meet and assign an officer a distinct utility score based on his prior jobs that he'd held and what it looked like he would be able to do. It accounted both for officer preference and the qualifications. We did weight the preference over the qualification as kind of designated by the Army. Each officer and branch or functional area pair had a distinct score. And then to mitigate subjectivity of the scoring, we tried to normalize them across all the panels because different panels were assigning scores to different subgroups of officers based on the fact that a single panel couldn't go through all the officers. It would simply be too much work. All right, and so we went ahead and we constructed a network model. You see here a small network. And so the nodes on the left-hand side represent officers. And so we have in this example I officers whom we wish to assign to either a branch or a functional area. And there would be an arrow between an officer node and a branch or functional area node if that officer could serve in that branch or functional area. We did assume that each officer could always serve in his basic branch, but then he could choose up to 3 functional areas in which to serve as well. And then we have another set of arcs from the branch or functional area nodes to the sync. And then on these arcs are various important characteristics of the model. And so on each arc between the first and second set of nodes, we've got the utility score. So if we assign an officer to a branch, then he gets a certain utility score based on him as himself being an officer and based on the particular functional area. So that was based on attributes of those 2 nodes. And then we have lower bounds of 0, upper bounds of 1, meaning we can assign at most 1 officer there because he is at most 1 person. And then departing from the branch and functional area nodes and going into the sync, we had minimum Army requirements and maximum Army requirements. So the total number of officers we were assigning to a branch or functional area had to be between the minimum and maximum number as designated by the Army. So this is a way of depicting the model. We were able to solve it very quickly based on this depiction, based on the fact it was a network and not like, for example, an integer program. All right, so again, we'll talk a little bit more about solution techniques and some results as soon as I finish discussing the next 2. So then we move to Coast Guard quickly. So Clearwater Air Station, at the time they were maintaining 9 Sikorsky H-860J helicopters at Clearwater. They were also responsible for deployments in 2 deployment sites off the coast of Florida. And the aircraft in general were used for medium-range recovery missions, mainly in this area at search and rescue, drug interdiction, and alien migration interdiction. So the heavy maintenance program at Clearwater was designed to mitigate the effects of the corrosive and abrasive environment of all the salt water and the sand. And so based on the flight hours accrued by each aircraft, they would go into a certain type of maintenance that would get progressively more aggressive as one accumulated flight hours until kind of a complete overhaul was done at 800 flight hours. And so within these inspection types, which got, as I say, more aggressive with the amount of flying time, there would be various inspection combinations, and so you perform some subset of these inspection combinations. That would mean that the aircraft would be down for a certain amount of time. This is, of course, all preventative maintenance. It's not, so it's scheduled. It's not the maintenance that would come up due to some emergency. So the idea is that over a 12-week horizon, we wanted to provide not just a schedule of how these aircraft were supposed to deploy, but also when they were supposed to go into maintenance. And we wanted to make sure that when the aircraft queued for maintenance or were sent into maintenance, that there actually wouldn't be a large queue of aircraft in front of them. Because prior to our model, what had happened is that all of a sudden the aircraft had flown their requisite number of hours, so they couldn't fly anymore, so they were grounded and they had to sit there because another 3 aircraft were already in maintenance and they didn't have time for more than 1 or 2 aircraft, depending on whether the extent of the maintenance was extensive or not, so depending on the flight hours. So we wanted to kind of stagger them in a reasonable fashion, and then when they weren't in maintenance, plan what they should be doing for their deployment. And then if we couldn't do that, we'd minimize the penalties associated with not getting them to a good deployment site or not having them in maintenance at the time without any weight associated with it. So Clearwater Air Station kind of operates in this geographic area I've depicted here, and so they had 2 secret deployment sites, so kind of the forward bases as well as just the majority of the aircraft were at Clearwater. Here goes a little guy who's undergoing some inspection, so he looks rather taken apart right now. And so those are the Coast Guard officers, and they're orange. And so when the plane went down in the Hudson, I think there's a line somewhere, kind of a title of an article, who are all those orange people and where did they come from? So they maybe came from here. All right, and so I have a model again. This is another integer program. It's just dealing with, exactly the constraints that I've described to you qualitatively in terms of ensuring that each helicopter during each time period is somewhere and accounted for. That would be the first constraint. We have various requirements of how many aircraft we need for each time and location, the 3 locations being the 2 deployment sites and then the home base of Clearwater. We also have requirements for the locations that aren't the home base as to how we'd like to allocate those aircraft. And so we don't necessarily want them hopping between one deployment site and another. We'd rather like them out at the deployment site for the majority of their time and then back to the home base. And so we have some constraints that dictate that. We also have constraints, anything with the X's in them are keeping track of flight hours, so that when the flight hours accumulate up to a certain point, then the aircraft is sent back for maintenance. We also have constraints on the maintenance facilities and the number of hours available there. And so those are the constraints you kind of see towards the bottom of the slide. More constraints just on interoperability and logical conditions associated with what the aircraft are doing, how many flight hours they have to have. There's obviously a minimum number of flight hours that they have to have before they go into maintenance, but you might rather send an aircraft in a couple hours early if it could avoid a queue later on. And so some of these constraints are associated with that. So again, a mixed integer programming model, and we'll talk a little bit later about how we solved it and what kind of results we got. So the fourth kind of topic in terms of finished topics that I have to talk about is the Navy topic. So we've done Army and Air Force and Coast Guard. Now we're up to Navy, optimizing the assignment of these Tomahawk cruise missiles to both surface ships and submarines. And so the Tomahawk is a long-range subsonic land attack missile. It can be launched from both of these platforms It flies a pre-planned route, so it's a smart missile. You can program it to go where you want it to go, and it can hit a target very precisely at a specified time. So a land attack strike order may involve quite a few Tomahawk missiles of different types. So in other words, ones that kind of would do different types of damage or that may have more precision in hitting a given target. You may also have numerous platforms at one time from which the Tomahawk missiles are launched. So the idea is that we wanted to build a tool to help Navy operational planners select really in real time some type of idea of which launch platforms, so which surface ships and which submarines, and not just which ones, but where exactly on those platforms the Tomahawk was located, because there's a number of different areas of these ships and submarines, and so in their inventory, and so you want to say this specific missile in the specific location, and that of course has some repercussions in terms of the operability of allowing simultaneous firing of Tomahawks aboard a single ship. I won't get into too much more on that, or it's all secret apparently. But clearly we also have individual platform capabilities that we consider, and also fleet-wide operational constraints. And then we have 8 goals. We've got this problem with the military planners telling us, well, we really want to do all these things, and so we really have a multi-objective problem here with 8 very distinct objectives. All right, so here we go. This is DG 67, I believe, the USS Shiloh, and in Operation Desert Strike, it launched 6 Tomahawk cruise missiles, and there goes one, as you see it. All right, so more math. This is another integer program, guess what? So we have all the goals written down here, and I'll just explain a little bit about what some of these goals entail. The first goal, and these are in order, I think, of what most people would consider priority, was simply to minimize the unmet tasking. So if you're supposed to meet these requirements, assigning the missiles to a given task for launch, you want to make sure that that's done to the extent you can. We wanted to also worry about how the missiles were being allocated. So there are a couple ways in which this was done. First of all, we wanted to ensure that ships leaving the theater and returning to home base had their missiles expended before ones remaining in theater. And then of the ships remaining in theater, we wanted to make sure that the tasking was spread out as evenly as possible among them, just to make sure for psychological reasons that they all felt they were playing in the game, but then also to ensure that if there was some failure and a ship went down, that it wouldn't have been the ship with all the tasking, so it's kind of to mitigate risk. The next 3 with these curious acronyms, RD, PR, and BU, is that we're looking specifically at where we're assigning what we call primary, ready, spare, and backup missiles. And so we're trying to make sure that these particular missiles are assigned in a reasonable way. So the primary is a missile that we really want to go ahead, and that's the idea of the notion of the missile we're going to fire. But we are required to have backup missiles. The ready spare is a backup on board the same ship as the primary task, and the backup missile is a backup on a different ship. And so if there's some weird reason and the primary missile didn't go, we have 2 forms of redundancy, and we had to make sure that those were all accounted for. We also wanted to ensure that this is the M cubed list in 7 that we've got with that little M3 there. So we have a various list of the taskings, and we are trying to ensure that the missile matched as closely as possible to what was given on the tasking requirement. We didn't necessarily want to use over-endowed missiles if we didn't have to. So you can always use a more competent missile for a target that doesn't require one, but that's not usually good because you're expending resources that you might need later. And then finally, we also had a way in which we wanted to kind of use missiles to maximize what we call the capabilities of follow-on salvo. That would simply be if there are certain ways in which we could fire missiles from a segment of a ship. And if we fired too many in certain ways, the follow-on capabilities would be less for a given ship in terms of simultaneous firing capabilities. So we had to kind of worry about how we were picking missiles on board a specific ship in terms of their location. So very specific kind of Navy-based requirements on this. And then we have a lot of constraints here just dealing with measuring numbers of missiles and how the missiles are chosen. And you see a zillion subscripts on the X. That's to choose the missile on board a particular platform. And then it also had to do with the type of missile, the time at which it was chosen, whether it was a primary, ready, spare, backup, and so forth. And so that's why we have all these different subscripts. Anyway, we also have constraints dealing with only choosing at most one missile to perform a given task, and other logical constraints, measuring the extent to which we don't meet the tasking, measuring the extent to which the missile is over-endowed or not, and measuring where the primary and ready spare are relative to the primary and the backup. You have to assign the ready spare to the same platform as the primary, the backup to a different platform. So everything that I've kind of talked about already, all went into the integer program. So now I want to spend a little bit of time talking about these four models and the ways in which they were solved. So clearly I could spend 2 or 3 hours just describing one model, the solution techniques, and the results, but what I'm going to do instead in the interest of time is simply make some broad statements about how these models were solved, because they're all integer programming models, or could be cast as integer programming models without special exploitation of the structure of the program. And clearly, you know, I mean, we can see in capital budgeting or personnel planning, you can't be choosing half a launcher, or, you know, assigning half a person to a particular job and so forth. So some of the things that we did in order to ensure that the models were actually tractable is we were looking at appropriate fidelity that deals with time. So making sure that the time increments are correct. If you have to kind of course a time increment, then you're not able to actually provide an operational solution. If you have to find a time increment, then the model is going to require a lot longer to solve, because a lot of the variables are based on time. So you're going to increase your number of variables if you decide that you need to know what's happening at every millisecond. So for capital budgeting, we decided that we didn't really need to have yearly fidelity in the out years. So in year 22, does it really matter if you're buying a launcher in year 22 or 23? So we tended to kind of aggregate time periods as we went out. Also, we might be able to aggregate constraints, such as those budget constraints, or there might be other constraints based on location that we could aggregate as well. We spent a lot of time looking at eliminating variables. So you don't just want, if you have a variable that has to do with all systems and time periods, you don't just want number of systems cross number of time periods variables in your problem. Instead, you know, you'd probably want to say, well, you know, there might be certain systems that can't come online in certain time periods based on the fact they're simply not constructed yet, or whatever the case may be. And so we went ahead and we eliminated variables a priori from the formulations, rather than having to put them, you know, constrained in, saying, well, you can't really do this, setting the variable to 0 and then eliminating it. That's very inefficient. We also relaxed certain variables from integer to continuous. You obviously have to be careful with this because, like I said, we can't assign half a person. But we can perhaps partially fund research and development initiatives in the capital budgeting model. So there's certain variables that sometimes we can relax. Other variables, such as in the Tomahawk model, we could relax to be continuous because they were the sum of binaries, and so clearly they can't be anything but an integer variable anyway, so we could relax those. Also, if we're dealing with long time horizons, sometimes we don't care as much about what's happening in the out years, and you start doing fractional things, it's still passable. We also had to deal with, so the constraint matrices. You saw a number of constraints that I wrote down in 3 of the 4 models. The other one I just had a simple network picture. But the coefficients, there can be a lot of those coefficients in the A matrix that are non-zero. And so we can use techniques in order to reduce the density of the A matrix. That means a lot of times you're creating more columns, but sometimes more sparse columns are better than fewer dense columns. We can look at cliques, clique cuts, cover cuts, Gomery cuts, mixed integer rounding cuts, and so forth in order to try and tighten bounds on some of the integer programs. And so we did that. We also made sure that when we elasticize the constraints, in other words, allow them to be violated with a penalty, which we did in most of the programs, certainly the capital budgeting model and the Tomahawk model, that we either bound those variables or we used them in constraints in a more kind of explicit fashion. So we certainly found that, there's a certain constraint about, in the Coast Guard model, about either you want to be at the same location at which you were at in the previous time period, or you want to be sent home for maintenance, and if not, you incur a penalty. Well, you can write that as the first constraint on this slide 22 pretty compactly, but if you split it up into two constraints and actually just apply the penalty to the constraint in which, if you're not at the same deployment site as you were in the previous period, that actually gives a lot tighter model. It changes things a bit in terms of the meaning, but the intent is reasonably close to what we wanted, and the model solves a lot better that way. The other thing is to recognize problem structure and try and exploit it. So certainly in the Army model, the personnel planning model, we recognized this could be a network, and so we got integer solutions for free, and so we cast it as a network. We looked at, cuts based specifically on NatStat constraints, like for the budgeting model. We tried to eliminate symmetry. You don't want a lot of objective function coefficients looking the exact same, or the algorithm will go ahead and spend a lot of time just kind of, weighing the pros and cons, the unquantifiable pros and cons of doing this in one time period versus that in one time period, and it all looks the same. So there aren't any clearly dominated or dominating solutions, and that's tougher for it to deal with. We also looked sometimes in constraints. The variables look similar, and we tried to deal with that. You may be able to use decomposition procedures for these. We didn't use any formal decomposition procedures in what we were doing, but that could come of use. We want to make sure to eliminate coefficients on big M's that look horrendous when we've got, some stuff is less than or equal to a logical variable allowing stuff to be positive times the extent to which it can be positive. You don't just want to say it can be infinity. There's usually a good bound on that. Sometimes we had luck with priority branching, branching on buying the launchers before the satellites were purchased in the Air Force model, or scheduling the deployments around the maintenance. So first scheduling the maintenance and then scheduling the deployments. It's more important to schedule a primary than a secondary task in the Tomahawk work, so we were able to do that. And there's a little bit of a caveat here that since this work is a little bit earlier, it's all been published, so it's kind of done. These are slightly earlier versions of C-Flex, probably ranging between about 7 and 11. Of course, in the newer stuff material I'll be discussing next, we're using a newer version of C-Flex, and things change over time in terms of what makes models solve faster. So I want to go ahead and just talk a little bit about the solutions here, and then after that we'll talk a little bit about the newer work. So this, for example, would be a sample solution for a capital budgeting model. They like these kind of stat graphs that you also see in energy, like in distributed generation or unit commitment. And so here, it was just kind of what types of things were they buying and what were they costing. And so we have kind of some type of scaled costs on the y-axis and then the year on the x-axis. You can see mission support kind of helping with morale plays a lot into this. But we have our space-based laser in there, fortunately, and we have space operations vehicle and infrared systems, launch vehicles, evolved expendable launch vehicles, and so forth. And then they were also interested in the extent to which these various tasks that were related to meeting some type of, national defense characteristics, how these tasks were actually being covered with the systems that were bought. And so you can see the extent to which this was done, and then the tasks are over on the, in the legend there, so this is what they thought, was important for the Air Force to maintain capabilities in. So of course, what I swept under the rug is the extent to which a given system covers a given task, or, where a system could cover more than one task. This is, of course, quite subject to debate, and so those numbers were quite qualitative and sometimes subject to a little bit of, controversy. But we just took them and moved along. All right, for the Army model, they were using this since, they have been using it since 1999, and so one of the lieutenant colonels, who's probably retired by now, just testified to the fact that they were using this, and most people were getting their first preference in the assignments there. And this is just a screenshot. We, dare I say, put this in Excel. For the Army, we used a solver, an open source solver developed by a, unfortunately now deceased professor at UT Austin in mechanical engineering and operations research. He had this, these nice add-ins for Excel, and so we used that in order to kind of bring this model to the Army. And so one sample run, you can see in the lower right-hand corner the extent to which the officers received their first preference. The majority did. Then we have second preference, third preference, and there are a few officers who didn't receive any of their preferences, but there were even more officers who didn't simply specify a preference, which is kind of interesting. But as we see, most officers are receiving their first preference. And over on the left is just kind of the columns of the input entries and so forth, the lower and the upper bounds. And then some summary statistics in the upper right there. So that was kind of what their tool looked like. The Coast Guard model, we were using C+9 for this, and we were able to get the solution times down to about a minute with thousands of binary variables and about 15,000 constraints. We ran the model with a reduced set of aircraft to justify a reduction in the flight time. Sometimes people, in fact, at the time we were doing this, Clearwater seemed to be getting a lot of its helicopters taken away, and the admiral would say, well, you just don't need this helicopter because you have 10. And they said, well, we do need it. And so we were able to say, well, look, you know, the deployments are going to have to be shorter in length. We're not going to be able to fly so many hours or give as much flight instruction back at the home base or whatever other things they were doing, simply because we do not have enough aircraft. And you can put this in a math model and show you can only do so much, and then there aren't enough hours in the day, no matter if 0 aircraft have to be queued at the maintenance facility and so forth. So we were able to use our model for that as well as just developing the schedules. The planner seemed pleased. And the other thing is that it was nice for them to have a tool rather than be worried about, well, we just seized like 1,000 pounds of cocaine and, you know, we've got like 300 illegal aliens trying to come in the country. Oh, by the way, please do the schedule. Like, this was not a very conducive environment for that type of activity, so having it automated and free of subjectivity and drama was very helpful to them. See, and so this is what one of the schedules looked like. And so the green is simply, we were looking at, you know, where they were at Clearwater, CLW, and then the red is when the aircraft are in maintenance. Some weeks you see 1 aircraft in maintenance and some weeks 2. It depends on the type of maintenance the aircraft is undergoing. The lighter maintenance schedules there allow for several, or 2 at least, aircraft to be in maintenance at once, otherwise it's a single one. And then the blue and the yellow are when the various aircraft are at the deployment site. And we had 2 deployment sites. So, and then, of course, the rows are the aircraft numbers, and then the columns are the weeks. All right. So for the Tomahawk model, again, we replaced the manual procedures they were using with something that was kind of reliable, and it could be used, again, in real time, you know, in operation, and kind of an operational theater that, again, might not be conducive to solving a brain-twisting problem. They kind of refined, you know, what they saw. We have a GUI I'll show you in a minute. So we demonstrated these capabilities to quite a few kind of naval bases. Then the contractor actually implemented the GUI, the graphical user interface for them. And it looked something like this. And so they imported their task lists. They could export a task plan. They could kind of click on the allocate button in order to perform the allocation. We wound up using a heuristic actually in the end to solve that integer program, and the details of that are in a paper that we published in a special issue in Naval Research Statistics. Okay, so now I want to spend a little bit of time talking about current work. And then this is maybe a little more qualitative. We obviously have math models behind this. But I chose here to spend a little more time just discussing, you know, the ideas. So first of all, we're looking at optimal course scheduling at the Air Force Academy. The students obviously are very time constrained in terms of performing their military duties, but also trying to get all their courses in. Of course, they can only take 4 years to graduate, so there's none of this, I couldn't get a course, so it took me 6 years to finish. Then there's other things they're very serious about physical education down there, so they leave a lot of the afternoon free for that. They also need to take these various airmanship courses. So This means that the schedules are kind of constrained, and students unfortunately don't always get the courses that they, show a preference for taking. There's a kind of outdated, greedy algorithm. It's quite undocumented. In fact, we showed it to a computer science professor, and he didn't even know what code it was written in, what language. So anyway, with no documentation and no real way of knowing exactly what's happening, we forged on. The solutions, they usually leave about 5% of student course pairs unscheduled, and then the scheduler, a person, has to invest some time to reconcile everyone in the scheduling conflicts. And so our approach is to formulate some type of course, mix it into your program in order to account for the restrictions on the student time and on the course availability and so forth. So we would like to determine appropriate number of sections to open of a given class to make sure that we're not opening sections with just 1 and 2 students in them, but also to make sure students get the courses they need. We have the department specifying a desired number of sections to be opened, and then we try and adhere to that as closely as possible. We also try and gather other information from the departments because sometimes you give them a solution and then they don't like it. So a priori, we try to get them to specify alternate acceptable periods in which to offer a course if we do need to bring another course online, unacceptable periods in which to offer a course, and the maximum number of sections based on their planning. We wind up solving this with this a sliding time window heuristic, and we perform successful solves based on the rank of a class. So we kind of try to schedule the seniors first and then the juniors and seniors and so forth. And we have something that works relatively well and tends to eliminate a lot of these unscheduled student course pairs. We're still kind of refining this a bit because my Air Force officer had to go to Korea for a year. So we're hopefully going to finish this. But one thing that he did that I thought was very instructive is he's able to generate kind of a number of section changes on the x-axis and the unmatched student course pairs on the y-axis, and really show the academy, if you want to get this number of unmatched student course pairs down to a negligible number, you're going to need to add more sections or change sections, and that may or may not be within your purview. And so, you can decide the extent to which you want to make these wholesale changes and, based on then the number of unscheduled student course pairs. And so you can see he's got various points labeled, beyond point, ignoring department course, offering time preferences. So you can only get down to 136 with the data we were using for a given semester. 136 unscheduled student course pairs before you start having to overrule what the department said as being, preferential for the times in which they'd offer more courses. Anyway, so that's kind of where we are there. We also have a follow-on to BRAC to improve the Army's decision analysis tool regarding stationing of Army forces and also the drawdowns, to take into consideration the drawdowns. So we have, again, an integer program to minimize the cost over time for the reduction and restationing of forces. The ideas we want to consider units, the demand for the various units, the personnel, and the limitations. We have to consider the facilities and the land requirements and the capabilities that they need to perform their operations. We obviously have budgetary restrictions as well. And so there are a lot of constraints we have in this model. So I've kind of detailed quite a few of them on the next 2 slides. We have to ensure that active units are assigned to an installation and that the capacity isn't exceeded. And that we have range training days for specific type of units, and those have to be honored in terms of both the requirements and upper bounds on the requirements. We heavy training land for some of the units. We need light training land for others of the units. We've got the fact that we don't really want to we've got about a 6-year model right now. We don't want to be reassigning units multiple times. We also have initial conditions to account for. Certain units can't move to certain installations. We have, other things on the demand for units at certain locations. Some installations we know they're going to close, and so the units have to have left by a certain time period. So we have a lot of these kind of requirements to consider. And so what we're trying to do is demonstrate the significance of capturing the input from the senior leaders to get all these constraints correct. Clearly, decisions are affected when we, the more time periods we're able to look at. And so we've got some scenarios from the Army we are looking at, but we also, this is a little bit kind of under construction because the next rack is not coming up for a little while, so people aren't running around with their hair on fire yet, but I'm sure they will be soon. And so the contrast with the previous base realignment and closure work, clearly we're updating all the requirements of the data and the structure of the map model, but we're also looking at both the reductions and restationing of units in a single model rather than handling them separately. All right, so I have just one final model. It's another Army model. So we had an Air Force model and two Army models here. This one, we were just at the Pentagon Center for Army Analysis talking about it. It's actually a combination of a statistical analysis and an optimization model. The idea is we want to provide an estimate of the number of forces required by year for counterinsurgency in a specific country, given the military, political, demographic, resources available and economic climate. So we want to establish a framework. It's going to be based on existing theories, and we also want to be able to test new theories. So one really has to get into the social science for this, and my student, Marvin King, has done so. But there are three existing theories about how counterinsurgencies evolve: the insurgent strategy, the type of insurgency, and the actor-centric theory. We found that either a hybrid of these theories or the insurgent strategy seems to be the best. So we had to do a lot of statistical analysis to establish that. And then the idea is that after we look at the theories, which should also tell us something about the variables we have to put in the regression model that are going to determine something about the number of forces, we use the following, this little graphic here, in order to say, well, yes, so we're going to send certain forces based on the requirements, and so we have kind of some notion of how we're going to increase and then decrease forces. There's also something that comes into play here called the expiration of national will, where that's our national will. So, we're helping a country like Afghanistan and Iraq, and at some point we say enough is enough, and then we withdraw. So this is all about us. In this case, how many forces should we send to the counterinsurgency to help the counterinsurgents fight? However, we have to adhere to the fact that beyond a certain point, we're going to kind of be tired of it, and we're going to leave, sometimes regardless of the outcome. And so what we do is we stuff all the statistics and these theories and kind of this notion of the expiration of national will into a mathematical program that's supposed to determine things based on some sets. We have forces, different types of forces in the country, clearly. We have different countries, and we have categories. Categories of the counterinsurgency, which we've determined from the statistical regression. And so based on that and these sets, we go ahead and we collect a lot of data about the national will threshold and various other indicators of the forces that go into the regression model, such as the GDP, the population of a country, and the force ratio required to reduce violence. And then we also have maximum numbers of counterinsurgent forces and the rates of the increase and decrease of the friendly forces based on the diagram I showed earlier, and then these various coefficients we've determined through our regression. So what we're really trying to do is determine the number of forces deployed at a certain time in a certain country. We have to also predict the number of deaths. And then we have some deviation variables, and we have a variable that tells us when the national will is met. So I didn't put the math in here, but this is just kind of a summary of the math in English. We're minimizing the deviation of the forces from what we required, and we need to account for all these things such as force to host nation population ratio, counterinsurgent to host nation forces can't grow faster than the maximum growth rate, can't exceed the maximum employable number. We've got kind of the logic to enforce the expiration of national will, and then what happens once we've met that. And clearly we have to put the regressions in there. So we have to determine the number of friendly deaths, which is a function of the various independent variables we've determined from the statistical regressions. So all that goes into the model as well to determine the X's, the number of forces to deploy. All right, and so that is the end rather abruptly. But those are kind of the 3 current models we're working on, and then the 4 previous ones are a little more polished with the results and actual publications. So I think I'm going to stop, and we'll see if there's any questions.
Okay, we didn't have any chat questions. I'm going to unmute everybody and see if we have any questions. Okay, any questions from the audience?
Okay, well, this is Jeff. Can you hear me?
Yeah, I can hear things.
Yeah, this is Jeff. I was curious on your helicopter model. Was the output of the linear program both a maintenance schedule and a deployment schedule for the helicopters, or what hours they should be used?
Yes, it was. So I will go back to my little output, which is on slide 29. And so, for example, in the upper left-hand corner, in the initial, well, week 0 is the initial condition for helicopter 6003. The idea is it was in clear water during that week for a certain amount of time, and so those were the number of hours, and so we somehow had 4 there. 4 hours of flight. So now what is exactly doing is, you know, I mean, they would decide, but it's there for that amount of time, so then what can they do? They can do flight instruction, they can do their own patrols and so forth. So we didn't manage it at that level, but we managed it at the level of this is the number of hours that you're going to be in a given place in a given week, and you're in the same place all week.
Got it. So it's prescriptive on the number of hours and then when that should generate a maintenance requirement.
Yes, exactly.
Yeah, interesting. Thanks.
All right, any more questions?
Yeah, I've got one more if nobody else is chipping in.
Okay.
Sure. Yeah, on your Army manning model, which I thought was interesting, I might have missed it, but I was curious what the origin nodes were on your network and why they were different. Were those different accession sources, or were those something else?
Those are people. So these guys here,
yeah.
1, 2, 3. Yeah, so I'm saying in this particular round, I'm assigning I people. 1, 2, 3 to I. So every single one of those was an actual officer. So that had an actual name to the node. So 1 was like John Smith or whatever. And so
Gotcha.
He could either go to, branch functional area 1 or 2, because apparently that was all he was qualified for. And so you'd either send 1, namely his whole self, to the first node or to the second node in the solution.
And this represents like a 1 round or an annual round of assignments or something like that?
Yes. Yes, that's correct. Yep. And then they were just doing this for the people who had been promoted, the officers who had been promoted to major and had to figure out who was going to functional areas and who was remaining in their basic branch. So it was just at that time of promotion to major was when this was being used.
Got it. Thanks.
Andrew, this is Norm Ryder. Thanks for the presentation. I thought it was great. It's just pretty interesting that School of Mines is doing this amount of military type of analysis, really good OR, so it's pretty neat. Appreciate you providing this, and I'd also be interested in if you wanted to share a little bit about, if you have time, about some of the other OR type of work that School of Mines is doing that might be outside the military or might be closely related, but you weren't able to cover. Is there any other highlights that you can provide?
Yes. So probably the biggest area of non-military work that could be applicable to the military is in the energy domain. And so specifically, I had an Air Force officer who's now in Afghanistan, but he was working on distributed energy generation. So the idea would be if you could retrofit a building, or if you were, looking at reducing your energy consumption at some sort of existing site, how would you go about reducing your reliance on the grid by having your own generators and so forth, for, kind of producing your energy? We had options to sell back to the grid in there, but, it would be a combination of things such as renewable energy sources and also maybe more conventional sources as well. And so the questions were, number one, what systems would you procure? And number two, how would you operate them in order to kind of minimize your costs, where we always allowed for the option of buying from the grid if we needed to, like in peak demand times or something. But in general, relying more on the technologies that were required for the specific site that would then be tailored towards that site. So there's been work on that. We've done some other things on unit commitment, but that's a little bit more like the wider grid, question. How do you turn your generators on and off? But those generators are providing energy for, a wide variety of sources. It's not quite as micro level. And then, I would say, and this sounds a little wild, but we work a lot on mining problems, production scheduling, and so forth. But there's a lot of insights there in terms of the mathematical structure and things you can exploit that you can use in military operations as well. And so often students are talking about the same type of things, problems with model tractability and formulation and so forth, whether or not they're doing a military problem or a mining problem. So I've done some general logistics in the past. I'm not currently working on anything right now, but clearly transportation models are also applicable to the military. So.
Great, thanks.
Yeah, you're welcome.
Yeah, I think that's about it for the questions.
Okay. I can send these slides somewhere, unless you already have them by virtue of the fact I'm on the webinar. I don't know.
Yeah, if you could please send them to me. This is Walt DeGrange, and then
okay.
I'll go ahead and post them with the brief, and I'll be sending out the announcement. This was recorded, and will be available to everybody next week.
Okay, yeah, that would be fine. I have no problem with that.